Hello, welcome to the fourth lecture on network theory. In the previous lecture, last lecture, we went through the concept of series and parallel connection of network elements, and we reduced or we solved a resistance network using the concept of series and parallel network connections. Okay, now let's move on with the next question. We will just start the lecture with one question. Okay. So again, we'll start with the circuit. So let's call this X, Y, Z, and what is this? This is U. Okay, U and A and B. Okay, so we have X, Y, Z, U, A and B. So the values of the resistance are 2, 3, 5, 2, 5, 7, 6 and 4. Okay, so this is the circuit. So the question is to find what? The question is to find this sorry, this is this Z comes here actually. This is Z, this is B. Okay, so the question is to find as in the last problem, R, X, Y, R, X, Z, R, X, U, R, Y, Z, R, Y, U, and R, X, A, R, X, B, and then R, Y, A, R, Y, B, and then R, U, X, U we have considered. So X, U and U X are the same, so we don't have to take the reverse. So U A, R, U B, R, A B. So you have to find all these. Okay. So I'll just solve some of them. So the remaining you will have to solve as homework. Okay. So let's start with R, X, Y. So R, X, Y means the flow will be coming through here, the current will be flowing through here, and we have to consider this. But current won't flow through this path, or current won't flow through this path, because current always requires a closed path to flow. That is, these are open paths. So again, current won't flow through this path, and current won't flow through this path. So effectively, if we want to find XY, RXY, only we have to consider this much, right? So let's redraw that to find RXY. Then it will be X we have marked here, and 2. We have 3, we have 2 and we have 5 and we have 2, right. So how will we write? So what does this mean? This means that it is a short circuit, right. Short circuit means when the current comes here, so it has a 0 resistance path through here, so it won't take the 5, it will just eliminate the 5, right. So this will be a 0 resistance path, that means this point is this point. So what is Rxy? Rxy equal to 2 parallel 2 plus 3, right, plus 3, it is equal to 4 ohm, right. 2 parallel 2 plus 3. So what is the next one we have to find? Next one is R exit. Let's do RAB, right. Let's do RAB. So we have done Rxy we have done, and we are doing RAB. So take another. RAB. So if we redraw the circuit for RAB, I am just directly drawing. Okay, B, A. This is 7, this is 5, this is 4, 2, 2 and 5, right. So again what happens? Again what happens? We have 2 and 2 in series, right. We have 2 and 2 in series, which is in parallel with this branch, right. This is parallel with this branch. But what happens here? This is a short circuit here, right. This is a short circuit. It means this point and this point are the same. This point and this point are the same. What does that mean? There is no potential difference between this point and this point. That is, no current will flow through this branch. So this is effectively this branch is effectively useless. This is not there. So this whole branch is useless. So the effective current will be flowing only like this, right. Therefore R AB is equal to 7 series with 4 series with 5 equal to 16 ohm, right. This is how it comes. We will just do one more example. So we did these two. This one we did, this one we did. So we will just randomly pick one more, and the rest you will have to do as homework, right. Let's take this R Y Z. Okay. It was R Y Z. Okay. Let's redraw the circuit for R Y Z. So what happens for R Y Z? Okay, this is the effective thing. Again, this is a short circuit, so this will be useless, and that means this point and this point are the same. So 2 and 2 will be in parallel, which will be series with 3. So R YZ is equal to 2 parallel 2 plus series with 3, that is 4O. Okay. So we did these three, XY, RXY, RYZ and RAB. So I'm just pointing out the homework here. RXZ, these two, whichever is marked using the red arrow, that is a homework. Okay. Okay, I use the concept of a short circuit, right? Short circuit. Short circuit means it has 0 resistance. R short circuit equal to 0 ohm. What does it mean? It means for a short circuit, voltage across the short circuit, is 0 volt. So if 0 voltage is there, 0 potential is there, then there is no resistance, right? There is no resistance. Okay. What is it? The next thing is, open circuit. Actually, it is not that way, it is the other way. When there is no resistance, no voltage will be dropped. Sorry, I just mentioned it the other way. Because there is no resistance, there won't be any voltage dropped across it. But I just said that there won't be any resistance because there is no voltage here, because that is the way we identify sometimes. We identify short circuit in network theory. When we are solving problems, we identify short circuits as points across which there is no voltage drop, and sometimes we conclude that because it is the case, it is a short circuit. Okay, anyway, the idea is that because there is no resistance, there won't be any voltage drop, and current, whatever current is there, it will flow. Okay. And for open circuit, our open circuit will be infinity. That is, there is no physical connection. There is no physical connection between the points which are open, right? For example, here for A and B, this is a short circuit. Here for A and B, this is an open circuit. That is, here it is a closed path. There is a path there without any resistance. But here there is not even a path. Therefore, no matter how much voltage you give, there won't be any current. Okay. So our open circuit is equal to infinity, and here I through open circuit is equal to 0 ampere. Okay. Okay. Now let's see a concept of Y delta transformation. Okay. The thing is that we have identified two things, right? What is it? Series and parallel connection. So there might be situations in which we may not be able to identify, or we may not be able to get any series or parallel connections. There can be situations like this. Okay. So this is some path, this is some connection will be there, this is some connection will be there. So let me call this as R C, R A, R B. Okay, so this is X, Y and Z. So here you cannot find any series or parallel connections. So then how will you solve this? Okay. So for that, what we do is we draw an equivalent connection. What we do is we change it into this. So this will be x, this will be y, this will be z. So basically whatever is in between these three terminals, we are converting it into something else, so that it will be easier for us. So let's call this R1, R2 and R3. Okay. So I am just going to directly write the equations for R1, R2 and R3. We have methods to find this. Okay, anyway, R1 equal to RA RC by RA plus RB plus RC. Okay, R1. Okay, suppose we can imagine this thing being coming like this. Okay, so R1 is coming here. So R1 equal to RA into RC divided by the sum. R2 equal to, so R2 is coming here, so it will be RA into RB divided by the sum, right? RA into RB, okay, RA RB divided by RA plus RB plus RC. Similarly, R3 is equal to, R3 is coming here, so RB into RC divided by sum. RB RC divided by RA plus RB plus RC. Simple. So what if it was resistance, instead of resistance, that is instead of RB, RA, RB, RC and R1, R2, R3, what if it were LA, LB, LC and L1, L2, L3? Okay, then what would have been it be? It would have been L1 would have been what? LA, LC, LA plus LB plus LC, and L2 similar to that, L3 similar to that. Just continue the logic. Okay, just continue with the logic. Similarly, if it would have been CA, CB, CC and C1, C2, C3, it would have been C1 equal to, no, we cannot write directly like that. Remember, capacitance we are taking sort of something like the inverse or opposite of inductance and resistance. So 1 by C1 would be equal to 1 by CA into 1 by CC divided by 1 by CA plus 1 by CB plus 1 by CC. Similarly, 1 by C2 and 1 by C3 will have similar equations. Okay, just bringing that to your notice. Now we can do the inverse also, right? So x, y, z, R1, R2, R3, if we want to convert it to the other way around, that is x, y, z, here it being RA, RB and RC, then RA would be R1 plus R2 plus R1 R2 by R3. To identify this, let's draw something like this. Okay, so RA is coming here, right? RA will be coming here. So R1 plus R2 plus R1 R2 by R3, right? Similarly, RB equal to, RB is, where is it coming? It's coming here. So R2 plus R3 plus R2 R3 by R1. R2 plus R3 plus R2 R3 by R1, and last one, RC equal to R1 plus R3 plus R1 R3 by R2, right? Again, similarly, for if we are considering LA, LB, LC and CA, CB, CC, so LA will be L1 plus L2 plus L1 L2 by L3. Similarly, LB something, LC will be something, and if it is a capacitance, what would be? It will be 1 by CA equal to 1 by C1 plus 1 by C2 plus 1 by C1 into 1 by C2 by 1 by C3. Similarly, 1 by CB and 1 by CC, right? So that is the case. So this conversion, I forgot to mention, this conversion it is called as a star delta conversion or delta star. You can or you can write this as delta star. Okay, this is the conversion, star delta, delta star, this way, both way. This is a symbol, this is just writing, no significance for either. Okay, so this is the delta, this is the star. We are just changing one configuration to the other for just for the ease of solving equations. That is it. Okay. Okay. Now that brings us to our last topic in this lecture, which is the voltage division rule and current division rule. So let's start with the voltage division rule. Division rule. Okay. So voltage division rule is applicable to series connection. Why is it applicable to only series connection? Because for a series connection, current is the same. Okay. So let's consider two resistances, R1, R2. We have the same current I, but the voltages are different, V1, V2. Okay. Just like the currents add up, the voltages will add up too. Okay. Here V1 plus V2 equal to V. Okay, just voltages add up, and V1 equal to R1 by R1 plus R2 into V, V2 equal to R2 by R1 plus R2 into V. That is, the voltage is dividing proportionate to the, that is, the total voltage is being divided into 2, and it is divided proportionate to the resistance. Okay, it is being proportionate to the resistance. That is, if you have more resistance, then more voltage will be dropping here, right? Similarly, if you have two inductors, I, V1, V2, L1, L2, we have the total voltage V, again V equal to V1 plus V2, right? So V1 equal to what will be? It will be always inductors and resistances when it comes to this voltage and current division and stuff like that. It behaves very similar. L1 plus L2 into V. V2 equal to L2 by L1 plus L2 into V. Very similar. So if you know resistance, then the inductance is pretty much the same. So how will it be for capacitance? It will be for capacitance C1, C2, we have an I here, V1, V2, right, and the total voltage is V. So again V equal to V1 plus V2, but V1 equal to how again remember capacitance behaves differently to that of inductors and resistances. So V1 equal to C2 by C1 plus C2 into V, V2 equal to C1 by C1 plus C2 into V. That is, if we are finding the voltage drop across here, it is inversely proportional to C1. That is, if it is not taking C1 in the numerator, it is saying C2 in the numerator, right. That is, the less capacitance here, the more voltage will be dropped here, something like that. Now let us take something similar to that of a capacitor, which is a conductance, right. So V1, V2, V. So V equal to V1 plus V2, V1 equal to what will be G2 by G1 plus G1 plus G2 into V, and V2 equal to G1 by G1 plus G2 into V. So capacitors and conductances respond the same way, or we model them the same way, and resistances and inductances we model them the same way. Okay, this is voltage division rule, and it is applicable to series connection. So logically, what will be the next thing? It is a current division rule, right. Current division, it is applicable for parallel connection. Why? Because voltage is the same here. So we have I1, we have I2, we have I, we have R1, R2. How will it behave? Right. Again, I equal to I1 plus I2, I am not writing that. I1 equal to R2 by R1 plus R2 into I, and I2 equal to R1 by R1 plus R2 into I. So here even if you look at the previous series parallel connections, equivalent resistance and so on. So here in a parallel connection, when it comes to the relation between resistance and current, it behaves in a similar way as capacitance and voltages behave in a series connection. Okay. So again, if we have an inductance like this, I1, I2, L1, L2. So I1 will be L2 by L1 plus L2 into I, I2 will be L1 by L1 plus L2 into I. Similarly, what will happen for capacitance? What will happen for capacitance? I1, I2, I, C1, C2. So I1 is equal to, remember here this acts like resistance acted in series. So C1 by C1 plus C2 into I2 equal to C2 by C1 plus C2 into I. So what happens if you are modeling the conductance, right? I1, I2, G1, G2. So I1 will be equal to G1 by G1 plus G2 into I, and I2 will be G2 by G1 plus G2 into I. Okay. So with this I'm stopping the lecture here. In the next lectures we will start with KVL and KCL, and we will do some more problems. Okay, so my request is that you go through this series and parallel connections, and again this voltage division and current division for all resistances and capacitance. So if you look at them, all of them side by side, you will be able to identify some patterns. Okay, so that if once you have that patterns in your mind, it will be easier for you. Okay, I have mentioned them, so just go through them. Okay, these ones. So this one was this was how we started. We started with a resistance network. I solved 3 of them. The rest are homework for you. Right. Then we discussed the concept of a short circuit and an open circuit. Okay. Then we went into star delta conversion, and this star delta conversion is a pretty handy thing to have when you are solving large networks. Okay. And then star delta and delta star, vice versa. Then we wound up our session with voltage division rule for series components and current division rule for parallel connection. Okay, thank you.